I thought it would be nice to just remind ourselves, just in case we're not too familiar with this area, about how a traditional address space and a virtual address space would actually look. So, even before virtual memory came about, you've always had physical address spaces where you actually have different components of the architecture occupying different portions of the address space. For example, the RAM, the read-only memory, the devices, and so on. You then had this extra layer of indirection called virtual memory, where the operating system would actually present a virtual address space to processes and would actually manage the translation of these virtual addresses to the underlying machine's physical addresses using a component of the architecture called the memory management unit, or the MMU. So the idea here is, the process would actually still make memory accesses using virtual addresses, but then the operating system would manage the translation of these virtual addresses to the underlying hardware's physical addresses. The translation itself is actually done with the help of this component called the memory management unit. The translation usually works in fixed size pages, for example, 4 kilobytes and so on. The translation also typically includes page protection properties, things like this page must only be read-only to the process, or this page must be readable and writable by the process, and so on. Simply because the translations can be so many, you typically have a cache of these translations in something called a translation look-aside buffer. The TLB basically caches the most recently used virtual to physical address mappings. This helps you in terms of performance. The MMU itself consists of various control registers like the page table location, the current address space ID, and whether you should be strictly checking for alignment or not, and so on, that help the operating system manage the translations of virtual address to physical address. The reason I talked about the virtual address space and the MMU in general is because we are actually going to be talking about virtualizing all of this support for the guest. So let's remind ourselves how a typical memory access looks. When a process uses a virtual address to make a memory access, it goes to the TLB. There can either be a hit or a miss in the TLB. If there's a hit, then you immediately get the translation of the virtual address to physical address from the TLB, and you're done with the memory access requirement. You basically pass the physical address to the memory controller, and you're done. If there's a miss in the TLB, however, there's actually a hardware page table walker that does the refill of this TLB cache with the appropriate mapping. And it does this refill by doing a walk of the hardware page tables, and that's why it's called a hardware page table walker. And it basically looks through the page table. It uses certain bits of the virtual address to actually do the lookup, and ultimately it comes out with whatever mapping sits in the page table, and then it refills this mapping in the TLB, and then you get a hit ultimately when you restart the instruction and you're done. When the hardware page table walker actually looks up this page table, if it doesn't find the mapping, it actually ends up raising what is called a page fault into the operating system's page fault handler. And the operating system itself might actually go and do a lot of other things, like it might have to page out and page in, it might have to do all sorts of other things before it can actually make that mapping valid and put in an appropriate virtual address to physical address mapping entry into the page table. And ultimately, it restarts that instruction, and then you ultimately refill the TLB and continue. The virtual address space itself used to look like this before we talked about virtualization. And I'm sorry about overloading the term virtual here, but that's traditionally how the operating system has called its memory abstraction to the process. It calls it virtual memory. We now have to virtualize that virtual memory support, and therefore we add yet another layer of indirection. And this is, the terminology here is a little bit confusing. The virtual address and physical address are really what the guest operating system itself manages in terms of its translations. And the machine address space refers to what I call the honest-to-God physical address space on the underlying hardware. So physical address space here is really not physical. It's just the view, from the point of view of the guest operating system, it's the physical address space. But it's actually translated into yet another space called the machine address space, which is the real machine addresses on the underlying hardware. And in terms of who manages which translation, the guest's operating system itself provides page tables to actually manage the translations between the virtual address and the physical address. And the virtual machine monitor itself, the VMM itself, has another data structure very similar to a page table called a FISMAP, which actually translates the physical addresses to the machine addresses. So the virtual machine monitor actually manages the underlying memory resources. It might decide to, dynamically allocate memory to the guest on an as-needed basis, on an on-demand basis. It might want to, for example, validate and invalidate these mappings as and when it desires. And this FISMAP data structure basically does the translation from physical address to machine address. So given that the guest manages one set of translations and the VMM manages another set of translations, it's important to note that the virtual address to the ultimate machine address is what has to be residing on the underlying hardware's page tables. Because ultimately, when you run the guest directly on top of the underlying hardware, the guest is going to make accesses using virtual addresses. The guest application is going to make accesses using virtual addresses. And you need to be able to translate those virtual addresses directly onto machine addresses on the underlying hardware for performance reasons, because you cannot have the monitor intervene at every guest memory access. That's just going to be insane. That's going to be almost equivalent to doing instruction interpretation. So if you want the virtual address to be directly translated to the underlying machine's machine address, one way of doing that would be to use something called a shadow page table, where the idea is you would actually have the hardware's page table walker point to this special data structure called the shadow page table, which actually translates guest virtual addresses directly into the underlying machine's machine addresses. And the shadow page table would actually keep shadowing what the guest is doing in terms of its page tables, its own page tables, and in terms of what the VMM translates in terms of physical address to machine address. This shadow page table is a data structure that has to be actively maintained and refilled by the virtual machine monitor. So let's look at how the exact same memory access proceeds in the case of a shadow page table. And again, just like in the previous graphical representation, I just want to clarify that a page table is not necessarily just one table. It's actually sometimes several levels, 3 levels, 4 levels, and so on. But just for simplification, I'm using just one simple table here to represent a page table. So just like before, the guest application is being directly executed on the underlying hardware. The guest uses a virtual address to make a memory access. The TLB receives this virtual address. If there's a hit, it directly gives you the underlying machine's machine address, and you provide that to the memory controller, and you're done. If there's a miss, however, the hardware page table walker, remember, is pointing to the shadow page table. And it does a lookup in the shadow page table to get this virtual address to machine address translation. And if it gets the mapping, it just refills the TLB like before, and everything is fine. If it doesn't find an underlying mapping in this shadow page table, it actually does, it raises a page fault to the virtual machine monitor saying, I don't have a mapping in your shadow page table. Go do whatever you need to do to refill this shadow page table, and then if you desire, issue a restart of this instruction, and then things will continue. And then when the virtual machine monitor itself gets a page fault, it actually has to do a walk of the guest's page table to actually look up the virtual address to physical address translation, because the virtual machine monitor has no idea how the VA to PA translation is done. That's all managed by the guest page table. And it does this page table walk in software, by the way, which is terribly slow. And once the guest page table walk is done, it gets the physical address. It then refers to its own data structure called the FISMAP or the PMAP, where it actually translates the physical address to the machine address. And in this case, again, if it does not have a physical to machine address mapping, it actually has to do whatever it needs to do, like maybe dynamically allocate memory now that the guest has made this access, and so on. And ultimately, once it gets the physical address to machine address mapping, it refills the shadow page table, issues a restart of the instruction, and then the TLB gets refilled and things continue. Along the way, however, if while the virtual machine monitor is doing a walk of the guest page table, it finds that the guest page table itself does not have a mapping existing in its page table, then the monitor actually ends up injecting a virtual page fault to the guest. And then the guest operating system does whatever it needs to do, like paging out and paging in or whatever else. So as you can imagine, there's a lot of complexity here. There's the virtual machine monitor itself managing the shadow page table and the fizz map. There's the guest managing the guest page table. There's the hardware page table walker walking the shadow page table, the monitor walking the guest page table, and so on. There's a lot of complexity here. The complexity, the cost of walking the guest page tables in software, the cost of the VMM entries and exits, all of these traps that happen whenever the shadow page table has an invalid mapping, all of these are the primary issues with shadow page tables. There's yet another problem that I'll not talk about in detail too much, but which is a very important problem in shadow page table management, which is keeping the shadow page table consistent with respect to the guest page table. Whenever the guest page table changes its mappings, or let's say validates an invalid mapping or invalidates a valid mapping or whatever else, you actually need to reflect those changes in the shadow page table. And keeping track of these changes and making sure that the monitor intervenes the least but yet manages to keep everything consistent is a very big challenge. Another way of doing memory virtualization, address-based virtualization, would be using something called nested page tables. And the idea here is very similar to how hardware-assisted virtualization was introduced to deal with the problems of trap and emulate, the problems with binary translation and all of that in the case of CPU virtualization. Very similarly here, because shadow page tables were a very complex way of doing things, they were costing a lot of performance, hardware vendors like Intel and ARM have actually come out with hardware support called nested page tables to actually deal with the problem of virtualizing memory for the guest. And the idea here is you just accept the fact that there are two stages of translation being performed here. One being the guest performing the translation of virtual to physical, the other being the virtualization layer or the monitor performing the translation from physical to machine. And you accept this fact, and the hardware itself has pointers to point to both of these translation tables, not just one. And the idea here is that the hardware itself would actually have walkers to walk through not only the guest, not only one page table that's pointed to, like in the case of shadow page table, but to two different translation layers. And the picture here becomes somewhat simpler than the shadow page table. The virtual address comes into the TLB like before. If there's a TLB hit, everything is fine. If there's a miss, however, the hardware page table walker actually walks through the guest page table. It gets the virtual address to physical address translation. And once it gets the physical address, it actually walks through this other layer of translation, which is managed by the monitor. And it comes up with the physical to machine translation, and it supplies the mapping to the TLB to actually do the refill. All of this is done by the hardware, by the way. There's no software involvement here. But and of course, like before, if it does not find a mapping in the guest page table, it raises a guest page fault. If it does not find a valid mapping in the fizz map data structure, it actually raises a monitor page fault appropriately, and so on. In which case, each of these layers would manage their own fault handling and so on. The big problem here is, of course, I was very simplistic when I said the hardware walks through the guest page table and gets a VA to PA translation. It turns out that the guest page table itself is specified in terms of physical addresses. And every time the hardware needs to access memory to get a value of that memory address, it can only use the machine address. Because remember, the underlying hardware, the memory controller, works only with machine addresses. It has no idea about physical addresses. And therefore, for every level, let's say there's a 3-level guest page table. For every level of reading the page table entry, the hardware actually needs to do a PA to MA translation. So it actually needs to do an entire walk of this second level, of this monitor level, every time it needs to read one entry in the guest page table. And this leads to what is typically called a quadratic walkthrough, which is a very highly complex, and it adds a lot to the walk cost of by the hardware. So as I said before, the picture looks much simpler than the shadow page table case. It simplifies the virtual machine monitor's own design. The monitor now does not have to have all these significant complexity routines to actually walk through the entire guest page table in software and all of that. There's no need for the monitor to maintain coherence between this one data structure called the shadow page table and another data structure called the guest page table and so on. So that's all very good and nice, but the negative, of course, is that the guest page table is in physical address space, and therefore the hardware needs to walk the entire FISMAP multiple times, basically every time it reads one page table entry in the guest's own page table, which is the quadratic walk I talked about. The hardware vendors like Intel and ARM have actually tried to somewhat deal with this kind of an issue by actually trying to do something called partial TLB refills and so on, where the idea is you would actually not have just a VA to MA translation cached, but you would actually have partial translations cached, and you would actually have, for example, if you want to read this guest page table, you already have the PA to MA translation sitting in the TLB and so on. So vendors have actually tried to deal with this complexity somewhat.
For software, for shadow page tables, I guess you would have the same problem. So is it that the software refill, the VMM, does the caching as well?
So let's see. So in the guest page table walk scenario, you're right that the monitor itself would need to refer to its own physical address to machine address translation every time it reads one page table entry in the guest when it's trying to do the walk in the software. But it turns out that that is done only when the shadow page table is has an invalid mapping, right? But in the case of the hardware walkthrough, it's done whenever the TLB has an invalid mapping, right? So the difference is in the shadow page table case. So let's say your TLB is very small for your workload, but your shadow page table still has all of your mappings, let's say. Only when the shadow page table is invalid does the monitor has to do a walk of the guest page table and install a valid mapping in the shadow page table and all of that, right? But when there's a valid mapping in the shadow page table, then everything is fine, because the only thing is the hardware has to walk through the shadow page table, but that's not a quadratic walk. When the hardware walks through the shadow page table.
The shadow page table is like a bigger cache.
Exactly. The shadow page table is as big as a page table can be. But the TLB depends on what kind of hardware you have, the TLB size. And in this case, whenever there's a TLB miss, remember, the hardware actually has to do the quadratic walk, not whenever there's a shadow page table miss like in the previous case. So that's the difference. I mean, the frequency of doing this is different, but you're right, the nature of having to do this quadratic walk is the same. It's just that in the shadow page table case, only when there's a shadow invalid mapping would you have to do this quadratic walk. Okay. Do you get the distinction?
Yeah,
Okay. The memory virtualization hardware assists, in addition to introducing nested page tables, also provide the monitor with its own address space, which actually eliminates the need for the monitor to actually sort of stealthily steal a portion of the guest address space and so on, having to hide itself and so on. Before sort of ending the concept of memory virtualization discussion, I thought it would be nice to look at one really cool application of doing memory virtualization. Because the monitor has the ability to interpose using memory virtualization, it can actually do some really cool things. One example is page sharing. The idea here is that if you have multiple virtual machines, let's say you're running 3 copies of Windows XP or Linux or whatever have you in 3 different virtual machines, you would tend to have the same code pages, sometimes the same configuration, sometimes the same metadata, and so on. And if you have exactly the same page contents, why should you have duplicate copies of those page contents sitting in memory? You can actually, if you are able to establish that the page contents are the same, using whatever mechanism you want, like doing fingerprinting of pages and so on, once you're able to establish that two page contents are the same, you can actually make them share exactly the same machine page on the underlying hardware using all of these different kinds of mappings. So the idea is both the guests' virtual addresses would be pointing to their own physical addresses as their own guest operating systems desire. But those physical pages can then be made to map to the exact same machine page by the VMM's FISMAP layer, because the monitor actually controls that layer and gets to interpose at that layer. And once you're able to do this, you're able to deduplicate those pages and therefore save a lot of memory consumption. And this has been used in a lot of different virtualization scenarios, and it has proven useful in many cases. There are really other cool applications of being able to interpose using memory virtualization, one of which is, for example, memory overcommitment, the idea being even if you have only this much memory on the underlying hardware, you can actually commit this much memory to the guest, and you can do an on-demand allocation of memory to the guest using this interposition, exploiting this interposition. So before I end this part of the talk, this part of the session, I thought it would be nice to touch on one topic that I've already sort of alluded to in my previous slides, which is the concept of ring compression. The idea here is that, remember the ring figure that I showed you, some architectures only have system and user, some architectures have 3 or 4 privilege levels, and so on. The monitor must actually share the guest's virtual address space if it wants to do things in a non-hardware assist world, if it wants to implement virtualization on a non-hardware assist world. And then it actually needs to install its own exception and interrupt handlers on the underlying hardware. It needs to, for example, have a translation cache if it's using binary translation. If it needs to have its own emulation routines, the code for the emulation routines sitting around. All of this must actually be accessible in the exact same virtual address space as the guest is in. And this leads to the problem where you need to be able to protect the monitor itself from the guest, because you want to enforce isolation. You want to guarantee that the guest is not able to do nasty things like scribble over physical memory of another virtual machine or of the monitor itself, and so on. You also, at the same time, need to be faithful in terms of the hardware interface that you're emulating to the virtual machine, which is you actually need to protect the guest kernel from the guest user, just like the guest would expect if it were to run on a piece of physical hardware. The problem here is you are essentially multiplexing the limited available memory protection mechanisms on the underlying hardware for 2 different reasons. One for protecting the VMM from the guest, the other for protecting the guest kernel from guest user. And it's as if you are compressing the available number of rings to a lesser number of rings. Like in this example I'm showing you, the VMM is in level 0, the guest kernel is in level 1, the guest user is in level 2, as far as this imagined virtual world is concerned. But when you are mapping this desired set of rings to the underlying hardware's available set of rings, which is only 2, you're essentially compressing the rings. And this leads to the problem where you still have to be faithful in terms of doing all of the page protection and let's say segmentation in the case of x86 and so on. All of the different memory protection mechanisms that are available, you have to keep emulating to the guest, while at the same time exploiting those very mechanisms on the underlying hardware to protect the monitor from the guest. And this itself is a very big challenge. And I'll touch upon this somewhat when I talk about ARM virtualization. But it's a very interesting topic by itself.